4 centuries before Christ, on a rocky island in the Aegean, a man dared to move the earth. Aristarchus of Samos looked at the heavens, the moon in its phases, the sun at its solstice, and asked, "What if we are not at the center?" It was heresy to some, absurd to most. The stars showed no shift. The ground beneath their feet felt immovable. Yet Aristarchus proposed a cosmos, where Earth spun daily on its axis and circled the sun each year. An idea 1,500 years too early. Aristarchus was born around 310 BCE in Samos, the same island that had given the world Pythagoras. His youth unfolded in a world reshaped by conquest. Alexander the Great's empire had cracked the barriers between East and West. Greek culture and ideas now flowed across Egypt, Persia, and beyond. In Alexandria stood the Mausoleum and the library, the greatest repository of human learning the ancient world would know. Geometry was the universal language, carried in the wake of Euclid's elements. To measure the heavens was to think in triangles. Aristarchus studied in this intellectual crucible, possibly under Strato of Lampsacus, head of the Peripatetic school, and within reach of mathematicians like Eratosthenes, the measurer of Earth. Here, astronomy was not a pastime of stargazers but a mathematical science, one step from philosophy itself. The prevailing cosmos was Aristotelian, Earth unmoving at the center, the heavens perfect and eternal, planets carried in crystalline spheres. Even those who doubted Aristotle, like the atomists, kept Earth still. To move it was to shatter the harmony of nature. And yet Aristarchus would dare. His surviving treatise is modestly titled On the Sizes and Distances of the Sun and Moon. But hidden in those pages is a revelation. The sun is vastly larger than the Earth. And if so, why should the smaller body command the center? To reach that conclusion, Aristarchus turned geometry on the heavens. With nothing but angles, eclipses, and shadows, he would redraw our place in the universe. Here was his reasoning. At the exact moment when the moon appears half illuminated, when day and night divide its face precisely in two, the angle between sun, earth, and moon must be close to 90 degrees. From Earth, you see the moon half lit only when the line to the moon is nearly perpendicular to the line to the sun. Aristarchus did not stop with the half moon and studied eclipses. When Earth casts its shadow on the moon during a lunar eclipse, the shadow is larger than the moon itself. By timing how long the moon takes to cross Earth's shadow, he could estimate that the moon is smaller than Earth, and its distance only a few dozen Earth diameters away. By combining eclipse timing, angular diameters, and geometry, he could derive the relative sizes: the moon smaller than Earth, the sun far larger, Earth somewhere in between, not master of the cosmos but a middleweight. It was not the accuracy of the measurement, but the implication of the scale that mattered most. If the sun was so much greater than Earth, why should the lesser body sit enthroned at the center? And so, from geometry, Aristarchus dared to imagine a sun-centered cosmos. Somewhere around 280 BCE, Aristarchus took the daring step. He proposed that Earth spins on its axis once each day and orbits the sun once each year. The moon orbits Earth. The stars lie at inconceivable distances. And the wandering planets, Mercury, Venus, Mars, Jupiter, Saturn, are not circling Earth at all, but fellow subjects in orbit around the sun. To grasp the shock of this claim, we must remember the cosmos that Aristarchus was upending. Aristotle's universe was orderly, Earth heavy and immovable at the center, celestial spheres carrying sun, moon, planets, and stars in perfect eternal rotations. It was elegant, moral, and widely accepted. Even alternative thinkers kept Earth still. The atomists, followers of Democritus, imagined infinite worlds, but placed Earth motionless at the center of ours. To move it was to violate physics itself. In Aristotelian thought, heavy bodies sought the center of the universe. If Earth moved, why were stones not left behind? Why did the air not rush past us like a storm? Aristarchus countered with simplicity. The heavens appear to turn once each day because Earth rotates. The sun seems to wander among the constellations once each year because Earth circles the sun. Retrograde motion, the strange backward loops of Mars and Jupiter, ceases to be a mystery of epicycles and becomes perspective, Earth overtaking slower planets in its orbital race. It was a model not of perfect crystalline spheres but of geometry and motion. For the first time, the cosmos was heliocentric. Yet almost no one believed him. We know of Aristarchus's heliocentric theory not from his own writings, but from later reports. Archimedes, in his treatise The Sand Reckoner, mentions it as a curious idea. Plutarch, writing centuries later, recalls that the Stoic philosopher Cleanthes accused Aristarchus of impiety for disturbing the hearth of the universe. The cosmos was not just science, it was philosophy, religion, even morality. To displace Earth was to displace humanity itself. There was another obstacle, the stars. If Earth truly orbited the sun, the stars should shift their positions as we move, a phenomenon called parallax. But to the naked eye, no such shift was visible. The stars appeared fixed, eternal. Aristarchus drew the only logical conclusion. The stars must be at distances so vast that the orbit of Earth is insignificant by comparison. He was right. But in an age before telescopes, this claim strained credibility. Infinity was a philosophical, not a physical idea. By the 2nd century CE, Claudius Ptolemy would codify a geocentric model so mathematically powerful, with circles upon circles, epicycles upon deferents, that it would dominate thought for 1,400 years. Aristarchus's sun-centered cosmos slipped into obscurity, a footnote in Archimedes. And yet, the audacity of it. 2 millennia before Galileo, before Copernicus, before Newton, Aristarchus had already conceived the essential outline of our universe. A spinning Earth, a sun at the center, stars flung across an unfathomable void. The first echo comes from none other than Archimedes. In his Sand Reckoner, a treatise attempting to calculate how many grains of sand could fit in the universe, Archimedes mentions Aristarchus. He notes, almost in passing, that Aristarchus of Samos supposes the fixed stars and the sun to remain unmoved and the Earth to revolve about the sun on a circular orbit. It is the earliest surviving record of heliocentrism. Archimedes did not endorse it, but he preserved it. And for that, we owe him the survival of the idea. Then came Hipparchus of Nicaea, a century after Aristarchus. Hipparchus built star catalogs, invented trigonometry, discovered the precession of the equinoxes. He, too, wrestled with the distances of sun and moon, refining Aristarchus's methods. Hipparchus criticized Aristarchus's values, finding them too small. He pushed the sun even farther, though still not close to the truth. But Hipparchus did not accept heliocentrism. Instead, he strengthened the mathematical scaffolding that Ptolemy would later inherit. By the 2nd century CE, Claudius Ptolemy in Alexandria forged the Almagest. With circles upon circles, deferents, and epicycles, he built a geocentric machine so accurate in prediction that it reigned unchallenged for over 1,000 years. In the grandeur of Ptolemy's model, Aristarchus's sun-centered sketch was reduced to a curiosity, a forgotten heresy. For medieval scholars in Byzantium, in the Islamic world, and in Christian Europe, Ptolemy was king. Aristarchus was a footnote. And yet, the footnote survived. When Nicholas Copernicus began to question Ptolemy in the 16th century, he searched the ancients for precedents. In his De Revolutionibus Orbium Coelestium, Copernicus mentions Aristarchus, cautiously, as someone who had once suggested the Earth moved. Copernicus knew that his ideas were radical, even dangerous. To find Aristarchus already there, long before, was both reassurance and inspiration. Thus the Samosian re-entered history, reborn in the Renaissance. Then came Galileo Galilei, with a telescope aimed at the heavens. He saw mountains on the moon, proving it was not a perfect sphere. He saw the phases of Venus, which could only be explained if Venus circled the sun, and he saw moons orbiting Jupiter, miniature worlds defying Earth's primacy. In Galileo's trial before the Inquisition, the heliocentric system became a matter not of mathematics, but of faith and authority. And what of the stars, that fatal obstacle in antiquity? In 1838, Friedrich Bessel finally measured stellar parallax, the tiny wobble of starlight as Earth orbits the sun. What Aristarchus had proclaimed in faith, Bessel confirmed in numbers. The stars were indeed at distances so immense that the ancients could not see their shift. 2,000 years late, the cosmos had vindicated the man from Samos. Aristarchus then measured the angle between the sun and the moon in our sky at that moment. He judged it to be about 87 degrees. Now he had two angles, 90 degrees at the moon, 87 degrees at Earth. The third angle, at the sun, followed from geometry. With these numbers, he applied Euclidean geometry. The result? The sun was about 19 times farther away than the moon. Notice what Aristarchus did not claim. He never said, The sun is exactly this many kilometers away. He couldn't. No one could. What he did was subtler and more powerful. He found ratios. The sun is to the moon as 19 is to 1. The moon is to Earth as so many diameters. With ratios, the cosmos could be compared and scaled, even if no absolute ruler could reach the heavens. But there was a trap in this method. The difference between 87 degrees and 89.5 degrees looks tiny to the eye. Yet in a triangle stretching millions of miles, that tiny error explodes into hundreds of Earth-Moon distances. Aristarchus' estimate of 19 was far too small. The real ratio is about 400. Still, the principle was correct. The sun was enormously farther away than the moon. And since both appeared the same size in the sky, the sun must also be enormously larger. The story of Aristarchus is one of disappearance and re-emergence. His bold heliocentric model faded into the dust of time. The sun-centered cosmos was buried beneath the weight of geocentrism, but echoes of Aristarchus remained. The preservation of Aristarchus' work depended on the same mechanisms that preserved the rest of ancient knowledge: the Library of Alexandria, the Roman Empire, and later the scholars of Byzantium. But for centuries, Aristarchus' name remained an obscure footnote in the history of science. In the Greek and Roman worlds, there were no scientific communities as we know them today. Works were copied, compiled, and translated by scribes, the ancient equivalents of our digital archives. Aristarchus' works passed through these hands but were not valued by many. By the time the Islamic Golden Age rose, his heliocentrism was buried deep. His name lived only in obscure mentions in the works of later mathematicians. The intellectual fire of the Renaissance was fueled by a rediscovery of ancient knowledge. Scholars scoured forgotten libraries, unearthed old texts, and reread the works of the ancients. Copernicus, as we saw earlier, found Aristarchus in the dusty annals of history. The great Polish astronomer saw Aristarchus as a precursor. In the early 1500s, Copernicus turned to the ancients for guidance. In his book De Revolutionibus Orbium Coelestium, he writes, "Some have said that Aristarchus of Samos first held the opinion that the Earth moved." He cites Aristarchus as the first to propose the sun's centrality, though he does so with a sense of caution, knowing how dangerous such an idea would be. But Copernicus's mind was already open. He was about to take Aristarchus's incomplete vision and mold it into a theory that would forever change the course of history. In fact, one of the great triumphs of Aristarchus's legacy lies in the mathematics of celestial measurement. His sun-moon distance ratios and his angular diameter method laid the groundwork for Kepler's ellipses and Galileo's observations of the phases of Venus. His influence echoed through centuries, even as the world rejected him. And it wasn't just the idea of a sun-centered system that persisted. Aristarchus's method, the application of geometry to the heavens, became one of the most powerful tools in science. The precision of his thinking would be taken up by future astronomers. From Eratosthenes measuring Earth's circumference to Galileo's observations of Jupiter's moons, the mathematical approach Aristarchus pioneered laid the foundation for centuries of discovery. Aristarchus's belief that the universe was governed by principles of geometry and ratios became the core assumption of later astronomers. His mathematics, though flawed in its measurements, opened the door to precision in understanding the cosmos. In the grand scheme of history, Aristarchus's name was overshadowed by those who came later. But his whisper, once unheard, reverberated through the centuries, guiding the work of those who followed. His work, lost to time, was rediscovered in fragments, and his ideas were rebirthed in the minds of thinkers like Copernicus, Kepler, and Galileo. It was Copernicus who, centuries later, found Aristarchus's name, a footnote to the future. Inspired by the ancient Greek, Copernicus resurrected the heliocentric theory in a new light. And then came Galileo, peering through his telescope, discovering moons orbiting Jupiter, showing that the universe could indeed hold multiple centers, and the Earth need not be at the center. Kepler refined the orbits of the planets into ellipses, and Newton explained why, all rooted in the very same ideas Aristarchus first dared to propose. In our quest for knowledge, we do not simply accumulate facts. We build upon the dreams of those who came before us.